Hello and welcome to class. In this video we'll be studying about angles in alternate segments, and this will mark the end of our series of studies on circle geometry. In the past few videos we've had to look at quite a number of circle theorems, and this is the last in our list of theorems, right? And that is the theorem of angles in alternate segments. But before we take a look at the theorem, let's try to refresh our minds on the concept of a segment. So a segment is simply, let's have a circle. Now when a line is drawn, a chord is drawn dividing the circle into two parts. What we are having is a segment. So we have this smaller portion here as the minor segment, and of course the bigger portion that we have up here as the major segment. So when a chord runs through from one end of the circle, one part of the circumference to the other, that chord divides a given circle into segments, major and minor segment. So when you're considering this the minor segment, the alternate segment to it is the major segment, and when you're considering the major segment, the minor segment to it, the alternate segment to it is the minor segment. That's how that works. Okay, let's take a look at the theorem of angles in alternate segment before we go ahead to illustrate that in a drawing. Now the theorem states that the angle between a tangent and a chord through the point of contact is equal to the angle made by the chord in the alternate segment. Let's try to highlight some keywords. The angle, so we have the angle between a tangent and the chord through the point of contact. That angle is equal to the angle made by the chord in the alternate segment. So let's make a diagram to illustrate this theorem. Alright, in other words, we need a circle and we need a tangent to that circle. Let's label it to be T, and then the point here A, let's say the X. And we need a chord that was going to make a contact with this tangent. So let the chord run from A. Let the chord run from A to this point, and let's call that to be B, somewhere here C. Alright, so we have chord AB and we have tangent TAX. Now the theorem states that the angle between the tangent and the given chord through the point of contact is equal to the angle made by the chord in the alternate segment. Therefore, this chord should subtend an angle in the alternate segment. Alright, so we have this. Chord AB is making an angle at point C. Now the theorem states that the angle between this chord AB and the tangent, that is the angle here between the chord AB and tangent TAX. This angle here is equal to the angle made by the chord in the alternate segment. Now mind you, look at it, this angle formed in between the chord and the tangent happens to fall within the region of the minor segment, as we saw before now. So the alternate segment to this minor segment is this bigger region. Alright, so the angle made by this chord and the tangent is equal to the angle made by the chord in the alternate segment, and that is the angle here. That is this point. In other words, we can say that angle BAX is equal to, that is the angle here, BAX is equal to the angle here, and that is, we can call that BCX. Alright, and the reason being that they are angles in alternate segments. So this is basically what the theorem is saying, that the angle made or formed in between a chord and a tangent is equal to the angle subtended or made by the chord in the alternate segment. Alright, so let's go ahead and look at some examples. In other words, if we should have a circle with a tangent, we have a chord subtending an angle in the alternate. Okay, so if there is a need for us to find okay, this diagram is a bit rough. Alright, so if we are given the angle here, if we are given the angle here, now it means that if we are given the angle here, maybe for sake of example, let's say we have here to be 40 degrees and we are looking for the angle here. By the theorem that we just looked at, it means that the angle here that we're looking for is also equal to 40 degrees because they are angles in alternate segment. They're angles in alternate segment. Let me also make a drawing to illustrate the other side of it. So if we have this and we have a tangent at this point, we have this chord here subtending an angle. Okay, so if we now remember that this chord as well can also choose to subtend an angle in the minor segment. Let me do that very well. Okay, so this chord, this chord, so this chord A, B, let me label that A, B, here is X, here is T, let's call here C. Alright, let's call that point here C. Now when we want to consider this value of the angle here, now the value of the angle here, that is angle TAB, now angle TAB that I've highlighted, that angle is formed in between the chord AB and the tangent TAX. Alright, and the theorem states that this angle formed in between them is equal to the angle formed by the chord in the alternate segment. Now the question becomes, where is the alternate segment? Remember that this angle happens to be formed inside the major segment, that is the bigger portion of the segment. Alright, so the angle that we're looking for should be in the minor segment, and that is the angle here. Alright, that's how that works. Okay, so the orientation could change, but the law or the theorem remains the same. Alright, let's look at some other examples, look at solve some problems and see how questions can come that will need us to use this theorem. So let me go ahead and make a drawing first of all. All right, now we have the drawing. We are looking for angle PTS. We're to find angle PTS. How do we tackle something like this? So we're looking for this angle here, PTS. How can we solve for that? Now when we consider the theorem of alternate angles in alternate segment, we can clearly see that angle TSR is alternate to angle RTQ. Alright, you see that angle, that angle TSR is equal to angle RTQ by the theorem of angles in alternate segment. Alright, so we can go ahead and note it that here is also 68 degrees. Alright, so there is 58 degrees, and since that is the case, now we have these two lines here, which is telling us that the two sides are equal. And when you know that your isosceles triangle, when you have two sides equal, it means that the base angles are also equal. Alright, so because of these two signs or two lines that we have here, which is indicative of the equality of those two sides, so it means that the base angles, that is the angles that we have here and here, are equal. Alright, no, so we can choose to call those two angles x because they are equal, they are same, their values are the same. Alright, so we can choose to call that x. Now the sum of angles in a triangle, remember that is equal to 180, so we can say that 68 plus x plus x should give us 180 degrees. That means that 68 plus 2x is equal to 180 degrees, and of course 2x, when we take away 68 from both sides, 2x is equal to 180 minus 68, and that will give us 112 degrees. And for us to get our x, we have to divide both sides by the coefficient, which is 2, and we have x to be equal to 56 degrees. Alright, so it means that the angle that we have here at this point is 56 degrees. Okay, so when we now consider the whole of this, so here we know is 56 degrees, here we know is 68 degrees. So how then do we get here? There are two ways we can get here. Now, one way is utilizing the concept of angles in alternate segment. When we consider this chord ST in this case has an angle formed between the chord and this tangent here. Alright, so it means that the angle that we have here is equal to what we have here because they are angles in alternate segment. That is one way we can find the value, and if that is the case, because the value of x is 56, it means that here also is 56. Alright, that is one way we can get what we're looking for. Or the second method we can employ is this: having or knowing that here is 68 already, here is also 56, Then for us to find here, when you combine these three angles here, that should give us angle on a straight line, and we know that angle on a straight line is equal to 180. So if we call here the angle we're looking for, that's angle PTS, to be A, so we have A plus 56 plus 68 to be equal to 180 degrees. All right, and when we solve for A plus 56 plus 68, all right, so A plus now 56 plus 68, that will give us 124 is equal to 180, and A is equal to, when we subtract 124 from both sides from 180, A becomes equal to 56 degrees still. All right, so we see that either way we are still correct. All right, either way we are still correct. Let's also try to look at another example. Okay, let me go ahead and make the drawing. That's 58 degrees there. That's 58 degrees. That's R. Here is S. Here is P. Let here be O. And let here be Q. So we are looking for QRS. We're looking for QRS. So find angle QRS. All right. So what we're looking for is this QRS. That is the whole of from here to here. QRS. Now the question becomes, how do we solve that? How do we calculate that? Okay, let's see it this way. Now, when we consider chord or line QR, consider this line here, QR, that is a chord. Then that chord is also, then when you consider this line here, that is a tangent. All right, and that means that there is an angle formed in between them. That is the angle here, and whatever angle that is formed here by the theorem that we are considering, that angle is equal to the angle made by the chord in the alternate segment. And where is the alternate segment? That is the whole of here. All right, so it means that the angle at this point is equivalent to the angle made by this chord, which happens to be here. So in other words, that means that here also is equal to 58 degrees. All right, that means that that point is equal to 58 degrees. All right, that's 58 degrees there. And if that's 58 degrees, so if angle, okay, let me call here x, so if angle QRX is equal to 58 degrees, for us to get angle QRS, the two angles all together must sum to 180 degrees, because that is angle on a straight line. So let's label the side we're looking for to be A. The side we're looking for, let it be A. So it means that A plus 58 is equal to 180 degrees, and A is equal to, taking away 158 from both sides, 180 minus 58, that will give us 122 degrees, and this is the solution. Alright, so the question can come in many forms. It is for you to try to understand, analyze the diagram, see which law applies. Not only this particular law, we've had to look at so many of the laws, like more than about 9 theorems. All right, we've had to look at 9 theorems of the from your circle geometry, talking about your tangents, 2 theorems on tangent, the angles in the same segment, angles formed at the center by a chord, angle formed by a chord at the center. We have looked at opposite angles of a cyclic quadrilateral. We have also looked at so many other laws. All right, so all those are theorems that we've had to look at. Each of them you have to gain mastery, be able to identify. That's the only way you have to be able to identify where they apply. All right, so like I've already said, this will mark the end of our series of studies on circle geometry. Okay, all right. So I'll be seeing you in the next video, but before that I would want you to try this particular assignment. Try to solve this, whether you can be able to like analyze it and give the solution. Okay, so here is 48 degrees. That's 48 degrees there. That's 48 degrees at that point, and here is 55 degrees, 55 degrees. That's 55 degrees. So okay, let me go ahead and label them. Here is S, here is X, here is Q, here is P, and here is R. So considering this given diagram, evaluate angle S, Q, X. Alright, so you have to find the value of the angle here. Alright, so try that out and get across the solutions to me. I'll be seeing you in the next video. Bye for now.